Today we're talking about optimization, kind of switching gears a little bit. We're still using the derivative. It's just helping us solve a different type of problem than we've been doing the past few weeks. So optimization is really cool. It's super applicable to the real world. I actually took a whole entire class on this in college. It was like an industrial engineering class that I got to substitute for one of my crazy math classes. So I was like, I'm all about that because it's actually applying to the real world. So use optimization for problems where you're trying to figure out what is your greatest profit that you could come up with. Maybe like you're making t-shirts and pants, and it costs you a certain amount to make each t-shirt, costs you a certain amount to make each pair of pants. You get a certain amount of profit from making t-shirts, you can make a certain amount of profit from making pants. What's the best combination of pants and t-shirts to maximize your profit? Or maybe you're trying to decrease your costs. You're trying to figure out how can you build something in such a way that you use the least amount of money or the least amount of materials. Or maybe you're trying to save time. How can you optimize your time, or the greatest distance? Whatever it is, these problems are basically you trying to figure out a maximum or a minimum. Like we're either trying to make something as big as we possibly can, or we're trying to make something as small as we possibly can. And it can be applied to a lot of different contexts. So our first example is we have a manufacturer who wants to design an open box having a square base and a surface area of 108 square inches. What dimensions will produce a box with maximum volume? So we are trying to design a box in such a way that the volume is maximized. Oops, scroll down way too much. First, let's draw a picture. So we have a square base box that has an open top. Here's our box. So let's say that the length of the base is x. Since the base is a square, the width is also x. And then we don't know what the height is, so let's call it h. And volume of a rectangular prism of a box is length times width times height, so it's x times h, which is x squared h. And we call this our primary equation. Because we are trying to maximize volume. So volume is our primary equation, because it gives us the formula for the quantity to be optimized. So whatever you're trying to maximize or minimize, that is your primary equation. So in this instance, it's volume. Okay, our word problem also talks about surface area. So we're going to set up another equation for surface area. And surface area in this open-faced box is going to be the area of the base. And then what we call the lateral surface area, which is the area of the four sides that are sticking up. So there's not a top, so we're not counting the top of our box. So the area of our base is length times width, which is a square, so it's x squared. And the area of the four sides, so each of these sides is a rectangle with a length of x and a width of h. So each of those four rectangles is xh, and we have 4 of them. And we know from our word problem that the surface area is 108. And surface area is our secondary equation. We're not trying to optimize surface area, but this equation is just going to help us solve for our optimum dimensions. So this is our secondary equation. It's just kind of like a helping equation. It gives us some important information that we can use. So because volume is what we are trying to maximize, we want to write volume as a function of just one variable. So what that means is right now we have volume as a function of both x and h. We want to get this all in terms of either h or in terms of x. So that way we can try and like solve for one of them. But if we have two variables in there, then it's just a mess. So what we're going to do is we are going to take our secondary equation and we're going to try and isolate one of its variables. So I can either try and get x all by itself or I can try and get h all by itself. I think it's going to be easiest to get h by itself. So if I'm trying to solve for h, first I need to get rid of this x squared. So I'm going to subtract x squared from both sides. I'm trying to get h all by itself, so I'm just going to divide by 4x. So height is 108 minus x squared over 4x. So what I can do now is I can go plug all of this stuff into this equation for h. I'm going to go plug 108 minus x squared over 4x into my primary equation, into my volume equation, substitute all of that for h. So when I do that, everything will be in terms of x's. So now I'm going to have volume is going to be x squared, and then in place of h, I'm going to put 108 minus x over 4x. So I'm going to have, this is technically x squared over 1. So this is in the numerator. One of my x's in my numerator can cancel with this x that's in my denominator. So I'll have x times 108 minus x over 4. I can distribute this x to both of the terms inside my parentheses. 108x minus x squared over 4. And then just trust me on this. You'll see why we're doing this in just a second. But I'm going to split this into two individual fractions. 108x over 4 minus x squared over 4. I can reduce 108 over 4. You'll have a calculator, so don't worry. 108 divided by 4 is 27. This is 27x, and then minus x squared over 4. Oh, I'm sorry. I just realized that this is 108 minus x squared. So this is x squared, this is x squared, this is x cubed. Sorry, I just copied it down wrong. This is x squared. I forgot that. Sorry. Hope that didn't throw anybody off too much. All right. The next thing we need to do before we go any further is we need to determine a feasible domain. AKA x values that make sense. So what I mean by that is, it doesn't make any sense in this problem for us to have lengths and widths of our box, dimensions of our box that are negative. Like x cannot be negative. It has to be greater than 0. So, like x, the length of our side, has to be greater than or equal to 0. Our volume also has to be positive. Our volume has to be greater than or equal to 0. It doesn't make any sense to have a negative volume. That is crazy talk. Okay, the next thing we can do is, we know that the surface area of this whole box is 108. So that means the area of the base plus the area of the 4 sides is going to add up to 108. So wouldn't you agree then that it would make sense to say, well, then I know for sure that the area of the base, of just the base, has to be less than my total surface area. So I can say the area of my base of our box has to be less than 108, because I still have to add in the 4 sides into the area of the base to get the total surface area. So area of the base is x squared. X squared has to be less than 108. So that means that I have to take the square root of that. So x is less than the square root of 108. So that would put our x value somewhere in between 0 and the square root of 108. Our x values have to be positive, but they can't be bigger than 108.